In this module, we will understand the thermodynamics of micellization. After studying this module, you shall be able to firstly know about the thermodynamic aspects of micellization using two general approaches for the Michel formation. Secondly, learn how to treat the Michel according to phase separation and mass action model to evaluate the thermodynamic parameters such as free energy, enthalpy and entropy. As mentioned earlier, the process of micellization is one of the most important characteristics of surfactant solution, and hence it is essential to understand its mechanism. That is, what is the driving force for Michel formation? This requires analysis of both the kinetic and the equilibrium aspects of the processes. Further, the laws of thermodynamics are applied to obtain the free energy, enthalpy and entropy of micellization. This will be followed by explanation of the driving force for Michel formation. Kinetic aspects. First, we will consider the kinetic aspects of micellization. Micellization is a dynamic phenomenon in which n monomeric surfactant molecules associate to form a Michel Sn. This process can be understood through equation 1, which says Ns is in equilibrium with Sn, where n is the number of monomeric surfactant molecules and Sn is the Michel. Hartley visualized a dynamic equilibrium in which surface active agent molecules are constantly leaving and entering the Michels from the solution. The same applies to the counter ions with ionic surfactants, which can exchange between the Michel surface and bulk solution. There are two relaxation processes for Micheler equilibrium characterized by relaxation times tau 1 and tau 2. The first tau 1 is of the order of 10 to the power minus 7 second and represents the lifetime of a surface active molecule in a Michel. That is, it represents the association and dissociation rate for a single molecule entering and leaving the Michel, which can be represented by equation as shown. S plus Sn minus 1 is in equilibrium with Sn. We have here K plus and K minus represent the association and dissociation rate constants respectively for a single molecule entering or leaving the Michel. The slower relaxation time tau 2 corresponds to a relatively slow process, namely the Michelization dissolution, which was represented by equation 1 as shown. 2 is of the order of milliseconds, that is 10 to the power minus 3 to the range of 1 second. Relaxation time tau 1 depends on the surfactant concentration, chain length and temperature. It increases with increasing chain length of surfactants, that is, the residence time increases with increasing chain length. The above discussion emphasizes the dynamic nature of Michel, and it is important to realize that there is a constant interchange between Michels and solution. The dynamic nature also applies to the counter ions, which exchange rapidly with lifetimes in the range 10 to the power minus 7 to 10 to the power minus 8 second. Furthermore, the counter ions appear to be laterally mobile and not to be associated with specific groups on the Michel surface. Let us learn about equilibrium aspects, that is thermodynamics of Michelization. Now we will understand the equilibrium aspects, that is thermodynamics of Michelization. Two general approaches have been used to tackle Michel formation. The first and the simplest approach treats Michels as a single phase and is referred to as the phase separation model. Here Michel formation is considered as a phase separation phenomena, and the CMC, that is the critical Michel concentration, is then the saturation concentration of the amphiphile in the monomeric state, whereas the Michel constitute the separated pseudo phase. The Kraft point is viewed as the temperature at which solid hydrated surfactant Michels and a solution saturated with undissociated surfactant molecules are in equilibrium at a given pressure. In the second approach, Michels and single surfactant molecule or ion are considered to be in association-dissociation equilibrium. In its simplest form, a single equilibrium constant is used to treat the process represented by the following expression: N is equal to V Michel divided by V, which is equal to 4 by 3 pi R cube Michel upon V, where capital N is the aggregation number, which can be expressed as the ratio between the Micheler core volume V Michel and the volume small v, which corresponds to the volume of the hydrophobic group in the Micheler core, that is volume of one chain, which can be further equated to N is equal to this, that is where R Michel is the radius of Michel. The CMC is merely a critical concentration above which any added surfactant appears in solution in a Micheler form, since the solubility of the associated surfactant is much greater than that of the monomeric surfactant molecules. The solubility of the surfactant as a whole will not increase markedly with temperature until it reaches the CMC region. Thus, in the mass action approach, the Kraft point represents the temperature at which the surfactant solubility equals the CMC, that is the critical Michel concentration. Now it is phase separation model. Now we will discuss this model. Let us consider an ionic surfactant in which N surfactant anions denoted as S and small n counter ions represented by capital M plus associates to the following expression, that is N S minus plus N M plus is in equilibrium with Sn. This is equation number 3. The Michel is simply a charge aggregate of surfactant ions plus an equivalent number of counter ions in the surrounding atmosphere and is treated as a separate phase. The chemical potential of the surfactant in the Micheler state is assumed to be constant at any given temperature, and it is called standard chemical potential, represented as mu 0m by analogy to a pure liquid or a pure solid. Considering the equilibrium between Michels and monomer, then we have the equation mu 0m equal to mu 01 plus RT ln A1, where mu 01 is the standard chemical potential of the surfactant monomer and A1 is its activity, which is equal to F1 x1. where F1 is the activity coefficient and X1 the mole fraction. Therefore, the standard free energy of micellization per mole of monomer, that is delta G0m, is given by, that is delta G0m is equal to mu 0m minus mu 01 equal to RT ln A1, which is approximately equated to RT ln X1, where F1 is taken as unity, which is a reasonable value in very dilute solution. The CMC may be identified with X1, so that the following equation becomes delta G0m equal to RT ln CMC, equation 6. This expression gives the standard free energy change in molarity scale. In equation 5, the CMC is expressed as a mole fraction, which is equal to C oblique 55.5 plus C, where C is the concentration of surfactant in mole per decimeter cube. Hence, substituting the value in equation 5, we get equation 7, that is delta G0m equal to RT ln C minus RT ln in brackets 55.5 plus C. This is equation 7. This expression gives the standard free energy change in mole fraction scale. Delta G0 should be calculated using the CMC expressed as a mole fraction as shown by equation 7. However, most quoted CMCs are given in mole per decimeter cube, and in many cases delta G0m have been quoted when the CMC is simply expressed in mole per decimeter cube. Strictly speaking, this is incorrect, since delta G0 should be based on mole fraction X1 rather than on C. Delta G0 obtained when the CMC is expressed in mole per decimeter cube is substantially different from that found with CMC expressed in mole fraction. This can be seen from the following example. For dodecyl hexaoxyethylene glycol, the quoted CMC is 8.7 into 10 to the power minus 5 mole per decimeter cube at 25 degrees C. Let us calculate the standard free energy change using both the mole fraction and the molarity scale. Hence, when the mole fraction scale is used, we get delta G0 equal to RT ln in brackets 8.7 into 10 to the minus 5 divided by 55.5 plus 8.7 into 10 to the minus 5, and the answer is minus 33.1 kilojoules per mole. This is our equation number 8. However, when the molarity scale is used, we get the answer as minus 23.2 kilojoules per mole. See equation 9. The phase separation model has been questioned for two main reasons. Firstly, according to this model, a clear discontinuity in the physical property of a surfactant solution such as surface tension, turbidity, etc. should be observed at the CMC. This is not always found experimentally, and the CMC is not a sharp breakpoint. Secondly, if two phases actually exist at the CMC, then equating the chemical potential of the surfactant molecules in the two phases would imply that the activity of the surfactant in the aqueous phase would be constant above the CMC. If this was the case, the surface tension of a surfactant solution should remain constant above the CMC. However, careful measurements have shown that the surface tension of a surfactant solution decreases slowly above the CMC, particularly when using a purified surfactant. Now coming to mass action model. This model assumes dissociation-association equilibrium between surfactant monomers and micelles. Thus, equilibrium constant can be calculated. For a non-ionic surfactant where charge effects are absent, this equilibrium is simply represented by the equation given by the aggregation number, as we have seen earlier, which assumes a single equilibrium in this case. The equilibrium constant Km is then given by equation as shown in number 10, that is Km is equal to the ratio of Sn upon S to the power n. The standard free energy per monomer is then given by minus delta G0 m equal to minus delta G by n equal to RT by n ln Km, and substituting the value of Km from 10 into this, we get equation 11. For many Micheler systems, n is greater than 50, and therefore the first term on the right hand side of equation 11 may be neglected, which results in equation 12, that is delta G0 m equal to RT ln S equal to RT ln CMC, which is identical to the equation derived earlier using the phase separation model. See equation 6. The mass action model allows a simple extension to ionic surfactants also, in which Michelle attract a substantial proportion of counter ions into an attached layer. For a Michelle made of n surfactant ions, where n minus p charges are associated with counter ions, that is having a net charge of p units and degree of dissociation as p by n, the following equilibrium may be established for an anionic surfactant with sodium counter ions as seen in equation 13. So, equilibrium constant Km will be given by the following equation number 14. Phillips has given a convenient solution for relating delta Gm to CMC, which arrives us at equation 15, that is delta G0m is equal to 2 minus P by n into RT ln CMC. For many ionic surfactants, the degree of dissociation P by n is approximately 0.2. So, equation 15 reduces to equation 16, that is delta G0m is equal to 1.8 RT ln CMC. Comparison with equation 12 clearly shows that for similar delta Gm, the CMC is about 2 orders of magnitude higher for ionic surfactants than with non-ionic surfactant of the same alkyl chain length, which can also be seen in the table. The table shows CMC values for various surface active agents, and CMC is given in mole per decimeter cube. In the presence of excess added electrolyte with mole fraction x1, the free energy of Michelization is given by the expression, that is equation 17. This equation shows that as mole fraction increases, the CMC decreases. It is clear from equation 15 that as P approaches 0, this happens when most charges are associated with counter ions, then the equation becomes 18, that is delta G0m equal to 2 RT ln CMC. However, when P approaches N, that is the counter ions are bound to Michel's, then the equation becomes delta G0M equal to RT ln CMC. Call it 19. This equation is the same equation as for non-ionic surfactants. Although the mass action approach could account for a number of experimental results, such as the small change in properties around the CMC, it has not escaped criticism. For example, the assumption that surfactants exist in solution in only two forms, namely single ions and Michel's of uniform size, is questionable. Analysis of various experimental results has shown that Michel's have a size distribution that is narrow and concentration dependent. Thus, the assumption of a single aggregation number is an oversimplification, and in reality there is a Michel's size distribution. This can be analyzed using the multiple equilibrium model, which can be best formulated as a stepwise aggregation as seen in equations 20, 21 and 22. As noted in particular in the analysis of kinetic data, there are aggregates over a wide range of aggregation numbers, from dimers and well beyond the most stable Michel's. However, for surfactants with not too high a CMC, the size distribution curve has a very deep minimum, the least stable aggregates being present in concentrations many orders of magnitude below those of the most abundant Michel's. For surfactants with predominantly spherical Michel's, the polydispersity is low, and there is then a particularly preferred Michel's size. Now we will understand how the enthalpy and entropy of Michelization can be calculated. The enthalpy of Michelization can be calculated from the variation of CMC with temperature. This follows from the equation, let us call it equation 23. The entropy of Michelization can then be calculated from the relationship between delta G0 and delta H0. As we all know, G is equal to H minus Ts, and therefore delta G0 is equal to delta H0 minus T delta H0. This is equation 24. Therefore, delta H0 may be calculated from surface tension minus log C plots at various temperatures. Unfortunately, the errors in locating the CMC in most of the cases is not a sharp point, which leads to a large error in the calculation of delta H0. A more accurate and direct method of obtaining delta H0 is microcalorimetry. The further table shows that delta G0 is large and negative. However, delta H0 is positive, indicating that the process is endothermic. In addition, T delta H0 is large and positive, implying that in the Michelization process there is a net increase in entropy. This positive enthalpy and entropy points to a different driving force for Michelization from that encountered in many aggregation processes. The influence of alkyl chain length of the surfactant on the free energy, enthalpy and entropy of Michelization can be seen from the table, which shows the function of alkyl chain length for sulfoxide surfactants. The results show that the standard free energy of Michelization becomes increasingly negative as the chain length increases. This is to be expected since the CMC decreases with increasing alkyl chain length. However, as you can all see, delta H0 becomes less positive and T delta G0 becomes more positive with increasing surfactant chain length. Thus, the large negative free energy of Michelization is made up of a small positive enthalpy which decreases slightly. The influence of alkyl chain length of the surfactant on the free energy, enthalpy and entropy of Michelization can be seen from the table, which shows the function of alkyl chain length for sulfoxide surfactants. The results show that the standard free energy of Michelization becomes increasingly negative as the chain length increases. This is to be expected since the CMC decreases with increasing alkyl chain length. However, delta H0 becomes less positive and T delta S0 becomes more positive with increasing surfactant chain length. Thus, the large negative free energy of Michelization is made up of a small positive enthalpy and a large positive entropy term T delta S0, which becomes more positive as the chain increases. Until now, we have understood the various models regarding Michelization process, but what are the driving forces of Michel formation and thermodynamic models? So, we will consider them one by one. Hydrophobic interaction, number 1. First is the, as I mentioned, hydrophobic interaction. We have returned several times to the important characteristic of surfactants and polar liquids, that is their amphiphilicity. Water does not interact favorably with the hydrophobic groups, and there is a driving force for expelling them from the aqueous environment. This may be achieved by a macroscopic phase separation or by hiding the non-polar groups in some other way. There are numerous other examples of hydrophobic effects and hydrophobic interactions. Let us see this diagram, which gives you the illustration of the effects of hydrophobic interaction, that is the tendency to eliminate contacts between water and non-polar molecules or surfaces. We can see in number 1, water and oil are immiscible with a strong driving force to expel hydrocarbon molecules from water. In figure 2, we see that self-assembly of surfactant molecules take place. Figure 3 shows other types of association of hydrocarbon chains which also takes place. In 4, folding of proteins occurs. In number 5, there is a strong adhesion between non-polar surfaces in water. Figure 6 shows non-wetting of water on hydrophobic surfaces. 7 depicts rapid coagulation of hydrophobic particles in water, and lastly number 8 gives you the attachment of hydrophobic particles to air bubbles, and which is a mechanism of froth flotation. For a hydrocarbon in water, there is a strong driving force for transfer to a hydrocarbon phase or some other non-polar environment. When a polar group is attached to the hydrocarbon, an opposing force is created which counteracts phase separation. If the opposition force is weak, phase separation will still result. If it is a very strong compared to the hydrophobic effect, on the other hand, the amphiphile will occur as single molecules or as small aggregates like dimers. It is the common intermediate situation with a balance between hydrophobic and hydrophilic interactions that we are concerned with the surfactant self-assemblies. The hydrophobic interaction increases with increasing alkyl chain lengths of an alkane or the hydrophobic group of a surfactant. Indeed, the decrease in solubility of an alkane with the number of carbons very much parallels the change in CMC, that is critical Michel concentration. Now coming to thermodynamical approach of Michel formation. As mentioned above, experimental results have clearly shown the Michel formation involves only a small enthalpy change and indeed is often endothermic. The negative free energy of Michelization is the result of large positive entropy. This leads to the conclusion that Michel formation must be predominantly entropy driven process. Two main sources of entropy have been suggested. The first is related to the so-called hydrophobic effect, which was first established from a consideration of the free energy, enthalpy and entropy of transfer of hydrocarbon from water to a liquid hydrocarbon. The table as shown here lists some results along with the heat capacity change delta Cp on transfer from water to a hydrocarbon, as well as Cp0, that is the heat capacity in the gas phase. The table also shows that the principal contribution to delta G0 is the large positive delta S0, which increases with increasing hydrocarbon chain length, whereas delta H0 is positive or negative with small magnitude. This large positive entropy is due to the fact that the water molecules around a hydrocarbon chain are ordered, forming clusters or icebergs. On transfer of an alkane from water to a liquid hydrocarbon, these clusters are broken, thus releasing water molecules that now have a higher entropy, and this agrees with the large entropy of transfer of an alkane from water to a hydrocarbon medium. This effect is also reflected in the much higher heat capacity change on transfer, delta C0P, when compared with the heat capacity in the gas phase, Cp0. The above effect is also operative on transfer of surfactant monomer to a micelle during the micellization process. Surfactant monomers contain structured water around their hydrocarbon chain. On transfer of such monomers to a micelle, these water molecules are released and they have a higher entropy. The second source of entropy increase on micellization may arise from the increase in flexibility of the hydrocarbon chains on their transfer from an aqueous to a hydrocarbon medium. The orientations and bendings of an organic chain are probably more restricted in an aqueous phase than in an organic phase. Notably, with ionic and zwitterion surfactants, an additional entropy contribution associated with the ionic head groups must be taken into account. Upon partial neutralization of the ionic charge by the counter ions, when aggregation occurs, water molecules are released. This will be associated with an entropy increase that should be added to the entropy increase resulting from the above hydrophobic effect. However, the relative contribution of the two effects is difficult to assess quantitatively. Let's have some general comments on amphiphile self-assembly. Aggregation in water and other polar solvents is due to the insolubility of the non-polar parts in water. The packing of the hydrocarbon chains result from the drive to minimize contact with water. Aggregation is opposed by the hydrophilic interaction, giving a repulsion between the polar head group on the micelle surface. The head group will arrange themselves to minimize the unfavorable repulsions. The self-assembly on an amphiphile depends on the strength of the opposing force. It must be strong enough to compete with one alternative, which is macroscopic phase separation, but must also be limited in magnitude, since otherwise the monomeric state will be in the most stable one. Examples of head groups giving amphiphiles that are too weak are hydroxyl, aldehyde, ketone and amine. For a long chain alcohol, macroscopic phase separation results rather than micelle formation. For ionic surfactants, the counter ion dissociation plays a major role. Because of the counter ions, macroscopic phase separation becomes entropically very unfavorable and there is a strong tendency to form small micelles. Co-solutes may affect amphiphile self-assembly in many different ways. They can, for example, stabilize the micelle by reducing the polar interactions. For ionic surfactants, we can neutralize the charge by adding an oppositely charged surfactant. We can screen the repulsions between head groups, or rather even out the uneven counterion distribution by adding electrolyte. Another way is we can also dilute the charges by introducing a non-ionic amphiphile like a long chain alcohol. However, in all cases we observe a marked reduction of the CMC and an increase in micelle size. Self-assembly and micelle formation have a much broader significance. Mixed polymer surfactant solutions have many applications, and it has become more and more evident that an important role of the polymer chains in many systems is to promote micelle formation. A macromolecular to solute will be much more effective in reducing the CMC than a low molecular weight one. Surfactant adsorption at hydrophilic solid surface is often pictured as leading to surfactant monolayers and bilayers, which can be visualized in the figure. These are the conventional pictures of surfactant adsorption at hydrophilic solid surfaces involving a monolayer and a bilayer structures. Now we will summarize what we have learnt in this module. The process of micelle formation is dynamic. This requires analysis of both the kinetics and the equilibrium aspects of the process. The thermodynamic parameters such as the free energy, enthalpy and entropy of micellization can be obtained from the equilibrium constant at different temperatures. However, the enthalpy of micellization is obtained more accurately from microcalorimetrically. Two general approaches have been used to understand the micelle formation. The first and the simplest approach treats micelle as a single phase and is referred to as the phase separation model. Here micelle formation is considered as a phase separation phenomena, and the CMC is then the saturation concentration of the amphiphile in the monomeric state, whereas the micelle constitute the separated pseudophase. In the second approach, micelles and single surfactant molecules or ions are considered to be in association-dissociation equilibria. The CMC is merely a concentration range above which any added surfactant appears in solution in a micellar form. Since the solubility of the associated surfactant is much greater than that of the monomeric surfactant, the solubility of the surfactant as a whole will not increase markedly with temperature until it reaches the CMC region. The phase separation model could not explain the discontinuity in physical property of surfactant such as surface tension and also the decrease in surface tension value above CMC. Although the mass action approach could account for a number of experimental results such as the small change in properties around the CMC, but the assumption that surfactants exist in solution in only two forms, namely single ions and micelles of uniform size, is still questionable. The negative free energy of micellization is a result of large positive entropy. This led to the conclusion that micelle formation must be predominantly entropy driven process. And we learnt earlier that two main sources of entropy have been suggested. The first is related to the so-called hydrophobic effect. This large positive entropy is due to the fact that the water molecules around a hydrocarbon chain are ordered, forming clusters or icebergs. On transfer of an alkane from water to a liquid hydrocarbon, these clusters are broken, thus releasing water molecules that now have higher entropy. This accounts for the large entropy of transfer of an alkane from water to a hydrocarbon medium. However, the second source of entropy increase on Michelization may arise from the increase in the flexibility of the hydrocarbon chains on their transfer from an aqueous to a hydrocarbon medium. The orientations and bendings of an organic chain are probably more restricted in an aqueous phase than in an organic phase. Notably, with ionic and zwitterion surfactants, an additional entropy contribution associated with the ionic head groups must be considered. Upon partial neutralization of the ionic charge by the counterions when aggregation occurs, water molecules are released. This will be associated with an entropy increase that should be added to the entropy increase resulting from the above hydrophobic effect. However, the relative contribution of the two effects is difficult to assess quantitatively.